Welcome again. Today we're going to look at Chapter 6, Introduction to Organic Chemistry. For those who aren't going to be moving on, this is going to be a bit of a treat. You're going to get the easiest part of organic chemistry that all the chem majors and biochem majors and like pre-nursing people are going to struggle through. You get that just brief background overview and kind of a peek into what they will have to suffer through in their sophomore year. We'll start this chapter with a demo. Just so we have a simple candle, a clean, dry beaker. I'm going to place this over top and see what happens. Immediately, we see beakers starting to fog up, catching the fumes from this flame. As it's lower and lower, it's starting to burn more blackly. Notice, you see what happened? I'll do it again. Despite I didn't touch the lighter to the flame, yet it relit. Let's watch. What happened is as this is burning, the fumes that is generated are combustible, and they followed the lit match, the lighter down, and relit the wick. Look at here, among other things, we see some char. We see we captured some incomplete combustion of the flame. Put this over here. Continue to hold it over there. So it's warming up. It's capturing CO2 and water, which is where it initially started to smoke, which is when it originally started. But as I put it lower and lower, the oxygen became less and less, and instead of fully combusting, it produced little ash particles, or incomplete combustion, that see that black smoke. And there's many other different tricks you can do with the flame, but that's just one. Let's try this one more time. Because all those, as this wax is melting, and then it's not actually the wick is burning, but the thing that's actually causing the heat and the flame is the wax itself, as it's going from liquid to gas, and liquid soaking up into that wick and turning into a gas burning. Our story starts with just the idea of organic chemistry and where it comes from. That in general, all life needs water and carbon to some extent. That without water, without carbon, nothing living on Earth would exist. Those three elements, the H, the O, and the C, are the three key components in all life. And so organic chemistry is just the chemistry of carbon compounds. Well, up until 150 years ago, all organic molecules had to be synthesized had to be, well, they weren't synthesized. They could only be isolated from things that were once alive or currently alive. You either had to get, for example, if you wanted silk, you had to get it from a silkworm. If you wanted butter or fat or oil, you or soap or whatever, you had to get it from some sort of animal. You had to get something from some plant. I mean, just look at ethyl alcohol. One of the key things that make life as an adult a lot easier for some people, at least. That comes from the fermentation of grains. Thus, it's also called grain alcohol. Soap. We get soap by rendering down fat from animals. And if you've ever watched Fight Club, you can do it from human fat as well. There's nothing wrong with that. Any type of fat can be rendered down into soap. In fact, one of the labs I used to do in chemistry class is to render down oil, like canola oil, plant oil, into soap. Is it the nicest soap? No, but can it be done? Absolutely. All of our dyes and our drugs were isolated from plants. As we'll learn later, well, or not, aspirin was isolated from willow trees. So it's found that a lot of these things can come naturally. Things like red orange henna comes from the Lawsonia shrub. Quinine, which is an anti-malarial drug. If you've ever had tonic, tonic is rich in quinine, but comes from the bark of a South American tree. So these drugs that we use and hear about all the time were all synthesized, were all isolated from various different plants and animals. And it was believed that all organic compounds had this vital force, that they had to come from something living in order for it to be, which is why we had to specify inorganic compounds, which compounds that did not contain carbon, and that they did not have to come from things with life. The inorganic chemistry is the chemistry of compounds that do not contain carbon. But we believed, well, this had to come from life, and this didn't have to come from life. So we had a distinct separation here. We're going to take urea as our example here of where the big change came. Urea, the compound on the far right, the CH4N2O, is one of the key compounds that we excrete in urine. It's a way of getting rid of the excess nitrogen that isn't used in proteins. It's about 2 to 5% of urine. That's probably responsible for a lot of the smell you notice if you haven't peed in a while. Well, we first isolated this in 1773, but it's thought we could only come from a body, not from a lab. That you would have to take someone's actual pee or some animal's pee and concentrate it down to get the urea. But in 1828, Friedrich Wöhler, in the bottom left there, managed to prepare urea by mixing ammonia, clearly inorganic, with cyanic, or it's actually isocyanic acid. Slightly different because it's how it's combined, but essentially we synthesized urea. We didn't isolate it from someone's body. We didn't concentrate it down. We took two compounds, mixed them in a lab, and produced a organic compound. It's the first synthesis rather than isolation, which is kind of ironic in a way because Wöhler was actually an inorganic chemist. He's also known for being the first person to isolate aluminum, boron, and silicon. But after that, organic chemistry kind of lost its sheen for have to be the vitality. There was no nothing really special about organic chemistry, which is why it's now just the chemistry of carbon compounds rather than chemistry of life. However, nowadays we've seen that organic has kind of regained its mystique, that you have organic food, organic drugs, and really everything is organic. You can make something in a lab and it's still organic. It's just whether it was natural or synthetic, really, is what the term should be. But once again, marketing comes into play here. Carbon is the key component here. Carbon, if you recall, has 4 valence electrons, thus is able to form 4 covalent bonds with up to 4 other atoms. As we'll see later, this doesn't have to be with 4 separate atoms, but there should be 4 bonds in order to give carbon an octet. With that in mind, we would call carbon tetravalent, from the Greek of tetra meaning 4 and valent from the Latin valentia meaning capacity, which language scholars would probably be cringing right now of the combination of Greek and Latin together in one word, but c'est la vie. Now, it's going to form strong bonds with hydrogen, with oxygen, with nitrogen, sulfur, halogens like fluorine, chlorine, bromine, iodine, and of course with other carbons. And when it combines with these carbons, it could either form in a linear straight chain or in branch chains, as we'll see. There's so much complexity that is possible depending on how we combine these carbon atoms and other molecules together. There is more than 10 million known organic compounds, and the number grows each day. But we can classify these compounds into what we call families. A family is just a classification of compounds with similar structures and similar property. Of these families, the main family we will discuss will be hydrocarbons. We're going to focus largely on hydrocarbons for the majority of this chapter. That isn't to say that we won't briefly discuss some of the other classifications, but for the most part, we'll look at hydrocarbons, which is compounds composed exclusively of hydrogen and carbon, thus the hydrocarbon. Within these hydrocarbon families, we can classify them as alkanes, alkenes, alkynes, and aromatics. We'll start by focusing on the alkanes and look from some of the simplest compounds to a little bit more complex. We'll start with methane, which is the simplest hydrocarbon containing only 1 carbon. Because it contains only 1 carbon, it must have 4 hydrogens attached to it. Unlike how we would draw this on paper, these hydrogens are not going to form a plus or cross. It's actually going to form a specific shape. This molecule contains 16 AMUs, can't get any smaller. So throughout this chapter, we will have to discuss stereochemistry, which is the arrangement of the atoms of a molecule in its 3-dimensional space. Because a lot of how organic molecules fit together will be how the stereochemistry is arranged. What the stereochemistry is, it's going to be a tetrahedral molecule, which a tetrahedral molecule is modeled after a tetrahedron, which is an equilateral triangle, 4 equilateral triangles all attached at the apexes or the corners. So it's essentially an equilateral pyramid where the base is also an equilateral triangle. The carbon in this case is going to be in the center of this tetrahedron, and thus the carbon is called a tetrahedral carbon. So tetrahedral carbon is a carbon atom that lies in the center of a tetrahedron. It forms covalent bonds with 4 atoms lying at the apexes or corners of this tetrahedron. A lot of the carbons we'll talk about are tetrahedral. Even though we won't draw it fancy like this every time, that is what is actually going to exist. Every time we discussed alkanes and carbons with 4 bonds to them, to 4 separate atoms, they are all tetrahedral carbons. Now, to help us see the next structure, we need to discuss the concept of a free radical. A free radical is just a chemical structure that contains an unpaired electron. So if we take that methane and pull apart a hydrogen and carbon bond, we'll make a hydrogen radical and a methyl radical. As we break apart this, the methane becomes methyl, where we change the ANE ending to a YL to talk about what type of group, what type of family we're having. Well, these radicals can do things. They are very reactive, and they tend to want to pair up to fill that electron shell, to give it those 8 or 2 electrons in the case of hydrogen. So if you put 2 hydrogen radicals together, they're going to snap together and form the diatomic hydrogen. If you have a chlorine radical, chlorine radicals are going to want to react. If you have 2 chlorine radicals, that's why you have chlorine as a diatomic. You put a methyl radical and a chlorine radical, boom, it's going to form that bond. Well, if I put 2 methyl radicals nearby, they would snap together and form a carbon-carbon bond. And that would make the second simplest hydrocarbon, which is ethane. It's a simple 2-carbon hydrocarbon. The molecular formula is C2H6, but the C2H6 doesn't really help us see the true complexity there. We could draw this in the expanded notation, as you see here, where all the bonds are intrinsically shown, or we could do and we will just have the condensed notation most of the time, where the hydrogen carbon bonds are assumed, and we're showing only the carbon-carbon bonds, that we can connect these chains together. With that in mind, oftentimes we'll just look at methyl, but we could also have ethyl groups. We could also have, as we'll get to next, propyl groups. And the basic hydrocarbon group is often abbreviated as an alkyl, because it's coming from the group alkane. So an alkyl group, where we put a generic R, that R could stand for any carbon chain. Now, if we combine the alkyl group with a halogen, like chlorine, it becomes an alkyl halide, generic RX. Like this is methyl chloride. If I put a bromine on ethane, it would be ethyl bromide. That they follow a generalized pattern. The alkane takes its root name with a YL, and the halide gets an IDE ending. Now, this is not really thought as ionic like the IDE would suggest, but it's just part of how we do the naming for these guys. The next one is propane with a molecular formula C3H8. C3H8. This C3H8 would then have, if we took off another molecule, you would have to CH3, CH2, CH3. Note that in the center, they cannot have a CH3, CH3, CH3. It has to have CH3, CH2, CH3, because carbon can only make 4 bonds. It is making a bond to one carbon, a bond to a second carbon, and that leaves 2 bonds open for hydrogen, and only 2 bonds. All of these guys are called alkanes. An alkane is a hydrocarbon whose molecular formula fits the general formula of CnH2n plus 2, meaning that whatever the number of carbon is, the hydrogen is twice that number plus 2. So C3, so that means 2 times 3 is 6, 6 plus 2 is 8. If I had C10, an alkane would be C10H22, because 10 times 2 is 20, 2 plus 20 is 22. This is the generalized name, but keep in mind, the only type of carbon an alkane contains is a tetrahedral carbon. The properties of these guys are all very similar. They're all odorless, they're all colorless, and they're very low in toxicity, that you can ingest a good amount of this without suffering any major consequences. Carbons chain 1 through 3 are all gases. While methane is the key component in natural gas, we typically don't use ethane much, at least in our case. Propane, you should all know, like, tell you what, we're going to use some propane and propane accessories. We got butane, which we use in our lighters, and some of the heavier ones start to get into oils and gasoline territory. And some of them even get to be lubricants. Because of the low toxicity, they can be, you can use it for things like petroleum jelly and mineral oil, which can be laxatives, among other things, that you can ingest this without hurting you. As I said, methane is odorless and colorless. All of these will burn or even explode in air. Methane is odorless and colorless, yet if you've ever smelled a natural gas leak, it had a smell. Why is that? Well, because when methane is 5 to 15% concentration in air, it becomes highly explosive. So when this is odorless and colorless, how do you tell it's in there to avoid any explosions? This can easily build up in a room and cause an explosion, or even asphyxiate anyone in the room because it displaces the air as it fills in. So what we actually do is we add a small amount of a sulfur group mercaptan, which has that annoying, like, rotten egg odor. And so when it's leaked, when methane leaks out, it's also leaking out a small amount of mercaptan, and you're smelling that. And, ooh, I better close off that valve. Almost all of these are used as fuel of some type. Even wax, in the wax and the candles are a type of alkanes. When we talk about methane, there's only one way to arrange those atoms. Not really complicated. Ethane, there's only one way to arrange those atoms. It's only you combine carbon 2 to carbon 1. But the thing of it is, when we get to propane, suddenly there's 2 different ways to combine that. You could add carbon 3 onto carbon 1, or you could add carbon 3 onto carbon 2. And while they look the same, it's technically a little different. It would be a little different. If carbon 2 had an isotope on it, we would have a completely different molecule. So we're making a different carbon to be the center carbon, depending on how we do that. The center carbon, the center CH2, is often called a methylene group. So what we're doing is we're taking a primary carbon and turning it into a secondary carbon. When we talk about primary, secondary, and tertiary, we're talking about how many carbons are attached to a specific carbon. So a primary carbon is a carbon bonded to exactly one other carbon. A secondary carbon, it's bonded to 2 carbons. So that center carbon would be considered secondary. A tertiary carbon is bonded to exactly 3. Now, there's none shown in this picture, but we'll see some later. And a quaternary carbon, which we won't really see because it's very uncommon, but it'd be a carbon that's bonded to exactly 4 other carbons. Why does this really matter? Because the next thing we're going to talk about is an isomers. A lot of organic chemistry has to do with isomers. The idea that different compounds that have the same molecular formula, but essentially have a different rearrangement of atoms, coming from the Greek isomeros, meaning equal share. Because just looking at propane. Propane has 2 primary carbons on each end and a secondary carbon in the middle. Butane could have 2 isomers. Propane has not really any isomers, but butane does. We could have the linear straight chain butane. So you see primary, secondary, secondary, primary. The boiling point of butane is negative 0.5 degrees Celsius. So it boils very easily, very, very easily. Isobutane, which is an isomer, that's the iso, has, we've, instead of made a straight chain, we made a branched group. So what happened? instead of adding to this propane, instead of adding a methyl to the primary carbon, we've added it to the secondary carbon to make a tertiary center group. The difference in this is that this boils at, instead of negative 0.5, it boils at negative 11.6. So it boils at a much lower temperature. So it's a lot easier to boil isobutane than it is to boil butane. Isomers, while being similar, often have a slightly different properties. And as we increase to larger and larger molecules, so will the number of isomers increase. We'll start by looking at how many isomers are possible with, as we'll see, pentane. Let's look at the possible isotopes of pentane. So we'll have to start by looking at, there are two different versions of butane and isobutane. That's butane. Now let's look at, well, where could we replace one of our methyls? Where could we replace one of our hydrogen with a methyl? If I attack here, there gets a linear straight chain pentane. So we went, if I attacked there, it would make the same molecule because it'd still be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that is one version of pentane. Now, instead of attacking the end, what if I attacked one of the middle, one of the secondary carbons? So if I attack here, that one, we have our isopentane, our 1, 2, 3, 4, 5. If I did the same, if I did it here instead, you'd have 1, 2, 3, 4, 5. Still the same molecule. So there's a third isomer, but I can't form it using butane. I have to use isobutane. So if I add the methyl to here or here, I've just reformed our isopentane. So the only, or if I did it there, it's still isopentane. The only place I could go is by taking this last hydrogen off and then adding there. Thus forms neopentane by putting the methyl group there. So that's our three different isomers. Now, we're going to spend a little bit of time in entomology, which is the origin of words, especially with chemical entomology, that we'll see a lot of these compounds have the same suffix, ane, ane, which refers to the family of alkane, but they all have a slightly different root. And the first four are all rooted from their unnatural origins. So there's a little bit of a story behind this, that methane was rooted from the group methyl alcohol, also known as methanol. In 1601, Robert Boyle discovered methanol by heating wood in the absence of air. That it caused the wood to decompose and to produce methanol without igniting. Now, between 1601 and 1930, the only way we could get methanol was through this destructive distillation of wood. And so it became known as methyl alcohol or wood alcohol, which, by the way, not good thing. It's incredibly toxic. If you ever drink that, it will quickly destroy your optic nerves and eventually lead to death. During the Prohibition, when people started running out of the cheap available sources of ethanol, some people started to try to distill down their furniture, and that left to high quantities of methanol, leading to death of the people who drank it. When nowadays we form methanol through reactions with natural gas and with coal, but that's how they formed it back then. So going back, the Greek origin, methyl would be wine and wood. So the wood of wine was our methyl. So the meth was a reference to the fact of that it came from the distillation of wood. F came from ethyl ether or diethyl ether, a very highly flammable liquid slash gas. It's, if you've ever read some of the really old Curious George, there is when George goes to the hospital, he ends up getting super high from breathing ether vapors. It was a disinfectant, among other things, a disinfectant and I think early anesthetic. Use that to kind of like dope people. But of course, it was also very, very, very flammable. Ethyl it comes from the ethyl ether. Well, the Greek word aether means to kindle, to burn, to shine. So this was a reference to the fact of how flammable ethyl ether was. How flammable ethyl ether was. And so we kept the term eth because of that. Well, prop, which is for our 3 carbons, comes from propionic acid. Propionic acid is an acid often found from fats and oils. We got that from fats and oils, one of the earliest acids found, which thus the Greek protos meaning first and pion meaning fat. So our first fat, the first acid we got from fat, so we kept the prop name. And bute comes from the Latin butyrum, which we come from butyric acid, which is often found in butter fat, and especially in rancid butter that gives it that unpleasant smell and rancid taste. Bute was kept from butyrum, which means Latin for butter. So that's where its original source. Even things like paraffin, like you've maybe heard of paraffin wax. Paraffin is often used as a generic source for our types of alkanes, but paraffin, Latin purum, barely or little, affinis, affinity or reactivity. The idea that these are not really reactive molecules for the most part, at least early on. They burned really well, but they had low toxicity and they didn't do much else. So paraffin wax, especially low burn, I mean, they burned, but not much else. As we progressed into the late 1800s, we started to take a more systematic approach, and we stopped trying to name things based on where it was first found. And so we started to use the Greek and Latin numbering system, where pent came from pent from pentane, come from the penta, Greek word for 5. Hex and hexane came from Greek hex of 6. Hepta and heptane, 7. Octane comes from octo, both in Greek and Latin, of 8. Well, nonane, novum, in Latin was 9. And decane came from the deca or decim, which was 10. So and from there we just keep numbering. So dodecane would be 12, and like pentadecane would be 15, and you can keep numbering like that. But we've kept, for whatever reason, these early terms, we've just kept them as a homage to like the early sources and the early naming. Now, here's where we start to get into some issues. Well, the isomers for the early compounds are very low. As we get into larger and larger compounds, the amount of isomers go up. And so the name iso, adding iso and neo to these compounds no longer suffices. You can do that with a compound that has 3 isomers, but how many names can you give to a compound with 5? How many names can you give to a compound with 9 without losing clarity? 18, 35. C15, there's 4,000 different isomers. C20, there's 366,000 isomers. And so we need a better way to name them. So in 1892, they had a convention in Geneva, Switzerland of the International Union of Pure and Applied Chemists to come up with a better naming system for these organic chemistry. They came up with a system called the IUPAC naming system that we still use today. While this is not the complete rules, this is simple enough for our purposes. Rule 1 is as the parent name for the compound. So as the root, use the name of the alkane corresponding to the longest continuous chain of carbon atoms. So if it's branched, you find what is the longest continuous chain. If you had if you went one branch and it was 5 carbons and one branch and 7 carbons, you would name it a heptane rather than a pentane. Locate the number of each group connecting to the chain by numbering the chain starting from the end. That will give the position of the lower number. So we want to give the lower number. If you can count from the left and the branch is on carbon 2, and you count from the right and branch is on carbon 8, you want to give the number with number 2. 3, indicate the total number of each set of mutually identical groups with a prefix. So if I have 2 methyl branches, you are going to have a dimethyl. If I have 2 ethyl branches, it's diethyl. If I have 3 propyl branches, it would be tripropyl. So we're going to tell how many different groups are coming off. If more than one group of each chain is present, give each group its individual location number. So when you count along there, what carbon is it located on? Then finally, as we write the name, we separate the numbers from each other by commas, and we separate the numbers from letters with a hyphen. So I'm going to show some examples of this in just a minute. But so this leaves off some of the things, like we'll talk about functional groups later. You actually typically alphabetize the groups coming off, but we're not going to worry about that. We're going to just do this simplicity. We're not going to be perfect because we're not aiming to be IUPAC organic chemists, but this is the generalized naming scheme for all organic compounds. Let's look at the naming of certain compounds. So let's just start with that guy. We can count here 1, 2, 3, 4, 5, 6, or we could count 1, 2, 3, 4, 5, 6, or we can count 1, 2, 3, 4, 5. Which one would have the longer chain? The longer chain would be 6. So this is going to be some sort of hexane. Doesn't matter which group is coming off, either whether we call that or that. This is an ethyl group. That's ethyl hexane. But where is it coming off? We could number, if we number from here, it's 1, 2, 3, 4. But if we number from here, it's 1, 2, 3. So we'd call it 3 ethyl hexane. It doesn't matter how funky it looks. What is the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. So this is a form of octane. What's coming off of it? So if I count, the lowest numbers would have 1, 2, 3, 4, 5, 6, 7, 8. So we have a methyl, another methyl, a third methyl. So it'd be trimethyl. And they're coming off at the 2, 4, and 6 position. So we call that 2, 4, 6 dash trimethyl octane. Longest chain is going to be probably 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we have coming off? We have an ethyl. We have 4 methyls. So looking at this, if I count it the other way, I think everything's going to be at a higher number. So we have 7 ethyl dash 3 comma 5 comma 5 comma 6 tetramethyl decane. So essentially we can name these and number them, and someone could figure that using that name, they could redraw this back out. Maybe a little bit prettier than mine, but they could draw that back out, which is why IUPAC is such a strong system. Now, there's a lot more complexities that we won't really worry about, but that is our start. Just like we removed a hydrogen radical to turn methane into ethane, what if we remove 2 hydrogen radicals from an ethane molecule? Instead of making a 4-membered ring, we can instead make a second bond to the carbon, So you have a carbon-carbon double bond. It'll make our first alkene. An alkene is simply a hydrocarbon that contains a carbon-carbon double bond. And it should fit the general formula of CnH2n. So there's twice the number of hydrogens as carbons. However, this only holds true if there is 1 double bond. As you add more double bonds, you have less and less hydrogens. However, this works for all general singular alkenes. So when we name guys with alkenes, instead of having the ane suffix, it would have an ene suffix. And this also leads to several different new isomers that could be formed. If you can put the double bond between 2 carbons, we number this based on the lower of the 2 carbons. We could put the double bond between the 1 and the 2 carbon of butane, and that would be 1-butene, saying the double bond is between the 1 and the 2. I could put it between the 2 and the 3 carbon, and that would be 2-butene. 2-butene. And then you're wondering, well, couldn't I put one between the 3 and the 4 carbon? Yes, you could. But remember, since we number this to give it the lower number, if you number this guy 1, 2, 3, 4, that's between the 3 and the 4. And I can number 1, 2, 3, 4. It's also between the 1 and the 2. So 3-butene would also be 1-butene. So we'd actually name it 1-butene again. So there's only 2 isomers that come from that, at least 2 different names. Now, we're not even going to go into diastereomers, so we'll leave that off for now. We can do that again. If we do that again, we can make a triple bond. We remove another HH pair. A triple bond is would form an alkyne, a hydrocarbon that contains a carbon-carbon triple bond, and would generally have a formula CnH2n minus 2. The most common alkyne we know is acetylene. Acetylene, which would be essentially ethine, which we use in welding with oxyacetylene torches. Now, alkenes and alkynes specifically have a little bit of a smell to them, unlike alkanes. You might have recognized ethene, whether you know it or not. It's an odor given off by fruit that actually speeds up ripening. In fact, some merchants will introduce ethane gas to try to ripen fruit before it's ready for market. Ethene or ethylene is 30% of all manufactured organics, is the 30% of all the organics made, which much of the ethylene will then go into forming types of plastics. Propylene, which would be the 3-carbon alkene, is another really large one, also going into plastics as well. These are example of olefins, these organic compounds with double bonds. The only triple bond one that see, as I said, was acetylene. Now, from there, we can classify these alkanes, alkenes, alkynes into two kind of subclasses. Saturated hydrocarbons, which a saturated hydrocarbon would be an example of an alkane, a hydrocarbon that has the maximum number of hydrogen atoms possible, will thus contain only single covalent bonds. So an alkane would be a saturated hydrocarbon. Unsaturated would be a hydrocarbon to which hydrogen could be added. An alkene and an alkyne have a double bond that could be split and then add hydrogen to it. In fact, it's very easy to add various groups to these. That you can, by mixing hydrogen and a catalyst, you can turn this ethene into an ethane. But with a little bit of acid in water, you could also turn ethene into ethanol. That we can add groups to that very easily because of the unsaturation. Now, unsaturated and saturated terms can also apply to fats and oils, which are simply long chain hydrocarbons that are attached to with an acid group on the end. But saturated fats would be just fats with no double bonds, essentially. And unsaturated fats have double bonds in there, whether it be at this group and making it bend this way with a trans fat or cis fat bending another way. And another type of compound we could look is cycloalkanes, where we cyclize the ring. Instead of doing a long chain or even a branch, we are bending around and binding it to the end. We can start with cyclopropane, cyclobutane, cyclopentane, cyclohexane, and you can keep going up and up and up. These compounds have the same type of formula as an alkene, meaning that this cyclization is one type of unsaturation. But we won't worry too much about these guys. Just know there's rings that we can see. That glucose is a form of a cycloalkane to some extent. And the last family we'll talk about is aromatic. The simplest aromatic, the most common one, is benzene, which it's a cyclohexene with alternating double bonds, where a double bond at 1, 3, and 5. But you can also draw it as at 2, 4, and 6 if you kept the same numbering scheme, but it technically still be 1, 3, and 5. Because this is so unsaturated, you'd expect it to be very easy to add hydrogen to it. But in fact, this is incredibly difficult to do. And that's because of aromatics have entirely different properties in them that stabilize this and make it very hard to add atoms to. In fact, because of this alternating double bonds and that they can swap back and forth, we actually look at the thing as a whole, the rings, it's just completely circularized in the center, that it's moving all the way through. Many plants that have aromatics actually have a very pleasant odor, which is why it gets the name aromatic. But we've taken aromatic to mean a compound that contains at least one benzene ring as part of its molecular structure. Now, benzene, the only aromatic is not benzene, but is the most common. And so we'll treat it as that for now. But cinnamon comes from cinnamaldehyde, which is a type of aromatic. Oil of wintergreen comes from has an aromatic. Oil of anise, also aromatic. And while we have all these types of families, they can intermingle. We can have paraffins with olefins in it. We can have triple bonds and double bonds in the same molecule. You can have long hydrocarbon chains, which all single bonds with a double bond somewhere in there. We can have rings, cyclo rings, mixed with double and triple bonds. We can have an aromatic and then double bonds. All these can intermingle to have a mishmash of different compounds. But all this was still hydrocarbons, where we'll get to finally functional groups. Functional groups are a small set of atoms held together by covalent bonds in a specific characteristic arrangement that is responsible for the principal chemical and physical properties of the compound. So all these alkanes are just the background. And then you can add on these reactive groups like an alcohol. Anytime you add an OH onto an alkyl group of any type, it becomes an alcohol. If you combine two alkyl groups over an oxygen, it becomes an ether. You put a halogen somewhere on there, it's an alkyl halide. All those we've kind of seen. Some of these we haven't really seen, or we've seen in passing if you've read the book. If you put a double bond to an oxygen followed by a hydrogen, so essentially a primary carbon with a C double bond O, it's an aldehyde. So in cinnamaldehyde, look for that C double bond OH. If you have a secondary type of aldehyde, so it's carbon double bond O carbon, it's a ketone. If you, instead of alcohol, have a nitrogen, you have an amine. If we have that C double bond O attached to an alcohol, it's an carboxylic acid or acid. If it's attached to an ether, it becomes an ester. And if it's attached to an amine, it becomes an amide. Now, there is actually far more functional groups than just these. These are just some of the more common ones. You'll see that each of these guys have very specific properties and very specific reactions based on the functional group. Part of organic chemistry is recognizing you cannot memorize every reaction for every single molecule. But what you can start to do is recognize a trend of this functional group does this in these situations, that all alkyl halides will like to do these type of reactions. All aldehydes will like to do these type of reactions. So if you start to recognize that, you can work with each functional group in turn. So I'd like to show you some molecules and show them with the functional group and see this in action. Now that we have some functional groups and we have some more complex families, let's see what we can recognize. Looking at these structures, what do we have here? We have a aromatic, we have a alcohol, and here we have a ketone, we have a amine, we have a cyclopropane, sorry, and we have a acid. In here we have a alkene, we have an alkyne connected by a ether. All these are some of our functional groups. Let's look back to our candle burning, the most common reaction that alkanes can do. When you react carbon and hydrogen in the presence of oxygen, it will form CO2 and water. CO2 and water, almost exclusively. Looking at the simplest form is we take charcoal and we react it with oxygen. What's it going to do? One carbon plus one oxygen forms one CO2. Now, if you do this in a low oxygen environment, what happens? If you don't have enough oxygen, that means more carbon is going to react with the oxygen. And so instead of forming CO2, you form two molecules of CO gas, which is a very deadly gas. CO2 takes a lot of it to harm you. CO, just trace amounts, which is why they tell you don't grill indoors. I don't care how cold it is, grill outside. Don't turn on the grill to warm up your room. That leads to death. It may start off by producing CO2, but in an enclosed space where there's not much ventilation, as it uses up the oxygen there, it's going to shift from making carbon dioxide to carbon monoxide, which will usually result in tragic results. Which comes to the last thing we need to talk about is balanced chemical equations. An equation containing the same number of atoms of each element among both reactants and products. One of the things we got to be able to do when we do chemistry is we got to balance the reaction. We have to look at, say, okay, in this case, starting one carbon and two oxygen, there should be one carbon and two oxygen on both sides. Two oxygen, one carbon. That works. Well, in this case, there's two oxygen here, and we split the oxygen has to split between two molecules because we have CO. So we need two carbons for both molecule. So two carbons, two oxygens, two carbons, two oxygens. So we have the same amount on each side. Same amount on each side. Now we'll look, one of the things we got to take into mind is the law of conservation still applies, that the amount of each atoms on both sides will always be the same. Let's practice balancing some chemical equations real quick before we finish up. Let's balance some chemical reactions. Okay, so one of the tricks to balancing chemical reactions is to never start with the oxygen, always finish with the oxygen. Oxygen appears in the most places, so it becomes harder to balance. In this case, we have one carbon here, so I'm counting my carbons. On the left, we have carbon, hydrogen, oxygen count. 1, 4, 2. My carbon, hydrogen, oxygen count right now is 1, 2, 3. Okay. The first thing I'm going to do is look at the carbon. One carbon, one carbon. It is balanced. Next thing I go to the hydrogen. 4 hydrogen, 2 hydrogen. So I have to add a coefficient of 2 to that. What that means is that 2 is going to be applied to that, 2 is going to be applied to that. So that becomes 4. That becomes 2 plus 2 is 4. Now, hydrogen is balanced. Hydrogen is balanced. Next step is to approach the oxygen. Oxygen 4, oxygen 2. How do I do that? I put a 2 here. And we have 4, 4, 4, 4, 1, 1. It is balanced. Let's try another one. Okay, with this in mind, now there's 2 carbons. So I must start by doubling that. It becomes 2, and that becomes 4 plus 1, 5. Because that's 6, I need to put that as a 3. That becomes 6. 4 plus 3 is 7. Here's where we have a problem. We have an odd number of oxygens on the left and an even number of oxygens on the right. I can start with a fractional number and try to balance it from there. But no matter what, I'm going to have to change everything. In order to change everything, I'll go ahead and start with 7 over 2. 7 over 2 times 2 is 7. Then it would be balanced. However, we're not allowed to have a fractional number here. So in order to take care of this fractional number, we are going to multiply everything by 2. So that means this becomes 2. This becomes 7. This becomes 4. And this becomes 6. So our numbers become 4, 12, 14, 4, 12, 14. We'll do one more. We'll do an alkene. Okay, start things off. Balance our carbon. 4 becomes 4. 4 times 2 is 8. 8 plus 1 is 9. Balance our hydrogen. That's 8. This is 2. So I have to multiply by 4. 4 times 2 is 8. 4 plus 8 is 12. So because that's an even number, you just can put this as 6. 6 times 2 is 12. Those are some quick examples of balancing chemical reactions. Finally, let's get to our prompt. I want you to find a simple plant or animal derivative that's greater than 3 carbons. I don't care what it is. Not really. You probably want to keep it semi-simple if you can, but I want you to describe it with your new organic lingo. Try to get it close to 150 words. This might be a little bit harder than your elemental one, but so I want you to give what is the longest carbon chain? What families are present? There could be more than one. It could be just a single family. What functional groups do you see? That's why I gave you so many functional groups to work with. So you don't be like, oh, I don't recognize that functional group. There might still be some that you don't recognize. There might be some you don't recognize. That's okay. Try to give its IUPAC name if you can. This may be a little bit harder, but feel free to include things like, where does it come from? What are its common uses? Also, please include a molecular picture as you submit that. I'd like to try to see what is the molecule you're trying to describe. I don't want to have to Wikipedia it if I have to. But so, essentially, simple plant or animal derivative, and try to describe it with our new chemistry terms. Well, next chapter, we'll talk about petroleum, which is a fancy hydrocarbon that is kind of important nowadays. Have a good day.